Okay, welcome back, all of you. I hope you had a nice break and thanks for the photograph. And also, again, I remind you, please do take part in that quiz or whatever we can call it competition because for the photograph identification because there are prizes for this. It is also down the memory lane for us, all of us. So you can identify the people, occasion, venue and everything. That will really be very nice for our archives people also. So having said that, let's go to second session of today. And I request Professor B.S. Acharya to chair this session. And there will be two talks. So Professor Acharya.
Language. Can I get this out? Chris, got it? Uh, sorry. Excuse me 1 minute. Yeah. So let me give you a little bit of the motivation for OT radio telescope. In the 50s, there were all these sky surveys, the telescopes, which are the dishes and things like that, which were got from the war. People are making surveys of the sky at high galactic altitudes at low frequencies. The 3C catalog at 170 megahertz was one of the reference catalogs at that time. The problem in radio astronomy is that all the telescopes are diffraction limited, so the resolution is very poor, lambda by d. So even a 45-meter dish or a 100-meter dish has got a resolution of only half a degree or worse at meter wavelength. So because of the poor angular resolution, the position was very not well known. And because of this, it's not possible to identify what the optical equivalent of the radio source was. Now, later years, people actually tended to go to high frequencies because lambda is smaller and you can get better resolution. But the science at high and low frequencies is very different. And if I keep talking about meter wavelength, it's because for the next 2-3 decades, the low frequency radio astronomy was neglected. There was nothing much happening. And everything was happening at high frequency. And this is a lacuna which actually QT telescope would fill. Now, since you had no optical identification of the source, you had no estimate of the distance, and so you had all these sources, hundreds of them. You have no idea where they were, what they are they near, are they far, are they strong, are they weak? And it was a mystery at that time. But radio astronomers were not prepared to sit quietly. They started to do statistical studies of these sources, famous log n log s curve. Essentially, if you look at the number of sources, it's proportional to the volume, which is proportional to R cubed. The flux of the source, if you think of it as a standard candle, decreases 1 over R squared. If we plot log n log s in a steady state kind of picture, it should have a slope of 1.5. Now, when radio astronomers looked at their data and made these plots, they found that they had a slope of 1.8, which created a lot of controversy. They concluded that there were more sources farther away, which is also in earlier epochs. And so the evolutionary model is required for explaining the data. Previously, you had two competing models, the steady state model where nothing changed, everything was same everywhere. And the evolutionary model from the Big Bang, which said that things will be changing, you can't expect things to be the same at all times. So this was a strong indicator for the evolutionary models at that time, which first kind of indication about this. So there's a lot of interest in knowing what are these radio sources? Are they really far away? Are they strong? Because people are questioning whether the whole methodology of this analysis. So the breakthrough came in studying lunar occultations and this discovery of quasars. The position of the ephemeris of the moon is known as great accuracy. So you know the position, the angular size at any with accuracy of any amount of accuracy you want. So if you see a source going behind the moon from the time of occultation, going behind and coming back, you can actually get a good estimate with a high resolution of the angular position of the source. So since all these 3C sources were known, people are actually using the lunar ephemeris to predict when they would get occulted within some uncertainty. And there was a prediction that in Australia, this 3C273, this 3C273 would get occulted a few times in 1962. And so these occultations were observed, and they got the position of the source great accuracy, better than a second of arc. And the optical astronomers could locate a source, a star-like object, which they call which became what was known as the QSO. And when they measured the spectrum of the source, they found it redshifted with a redshift of 1.58. Now, as you know, once you have a redshift from the Hubble distance relation, you can get a distance. And both the redshift and the distance made this one of the most distant sources known at that time. And it's also a very bright source, so it is also most luminous. And so suddenly the radio sources became very interesting because they were one of the most luminous objects in the sky. Now the beauty of it was that for studying lunar occultation, all you needed was a large collecting area and the ability to track. At that time, most of the large collecting areas and tracking sources were actually two-dimensional dishes, parabolas, which are very costly to build. It's much cheaper to build a cylinder, which is just as good for lunar occultation, but it costs much less, but it requires some extra electronics to do what is called phasing, which I'll explain in a minute. So this is what inspired Swaroop to propose a telescope to study lunar occultation, to just survey the sky using lunar occultation. Other studies were essentially targeted to, I know a source which is going behind, so I'll study it. Here he wanted to make a blind survey, statistically, no bias, just pick up whatever gets occulted, and that's an unbiased sample of sources. Statistically, that is what is required if you want to make any proper study. So to get this large collecting area, he proposed to have a cylinder, which is half a kilometer long, 30 meters wide, mounted with an effective area of 8,000 square meters. Visitors at Ooty would tell them, yeah, this telescope is 4 times the size of a jodel bag dish, which is one everybody knew at that time. So we didn't tell them that sensitivity is more than just collecting area, but it was not required. So the telescope is made equatorially mounted by essentially mounting it on a north-south hill, whose slope is the same as the latitude of the place, because of which the axis of the telescope becomes parallel to the axis of the Earth. And just by rotating the cylinder on its axis, you can follow it, track its source. After some survey of South India, they came up with a place, and this is possible because India is close to the equator. You couldn't do this in Europe and places like that because the slope will be too high. So with some survey, they actually found a place in Ooty, 11 degrees latitude, and after this thing, I mean, Ooty was also, people were familiar with it because Cosmic Ray was doing something there. And so they said on this, and they started construction between 1967 and 1970. A parabolic dish, you see, all the radiation comes to the focus in phase because of reflection and propagation. But for a cylinder, you have essentially a line focus. And so what you need to do is on this line, you have to all this, you have a bunch of dipoles at the focus. And by adding the signal from all the dipoles with appropriate phase differences and phase and delay compensation, you can actually form a beam or a point of focus in different parts of the sky. So a complicated system of electromagnetic and mechanical phase shifters was generated. Essentially, the signals from all the dishes are now combined with some appropriate phase shifts, because of which you could essentially get a beam which in the north-south direction would go from plus minus 30 degrees or a little more. The frequency of telescope was 327 megahertz, resolution was 2 degrees east-west because the telescope is only 30 meters, and 5 minutes of arc in the north-south, and you can track for 9 hours. You can see the telescope in the west, in the east. It's a very impressive thing to see it rotating, trundling along. And this is where the focus here of all the dipoles. This is a picture of construction of Ooty telescope. You can see ground being broken by MGK Menon, and at various stages, dishes going, the cylinders going up. They're going up. Many of them have come up. You can see dipoles here, and finally, in 1970, things have started to work. So let me come back to lunar occultation a little bit. The first occultation observed at Ooty was on February 18, 1970. This was 3C22 22.21. Unfortunately, I could not locate the original trace for that, but at least I've shown you a source getting occulted, a strong source, point source. You can see these frontal fringes, diffraction at the edge, which is what you see for a typical lunar occultation. If you look at this picture here, you can see at this time, the source is getting occulted. So you know the position of the moon. At this time, it's coming out. Again, you know the position of the moon. You know the diameter. So you draw the circle, they intersect at some point. That is the position. And the moon's position is known accurately. So you know the position of this to a second of arc. You also notice one thing, that when the source is getting occulted, the edge of the moon is crossing the source in one direction. When the source is coming out, the edge of the moon is coming out in a different direction. And so you essentially get information at different position angles. During immersion, you would see it as a double source. During immersion, you would see it as a single source. And from this, you can get two-dimensional information about the source. Also, if you look at the UT beam is very wide, 2 degrees in the north-south, but is very narrow in the, 2 degrees in the east-west, but is narrow in the north-south. So essentially, the UT telescope picks up fixed regions of this moon, and 12 beams covering it covers the whole moon all the time, and you simply keep following the moon as the moon trundles along in the sky. So regular observations tracking the moon for 9 hours goes on for the next decade or so. And typically every day you would see 1 or 2 new sources. Many of them are very routine, boring sources, but some of them are interesting. But this is what you need to do if you want to get a statistically stable sample. So occultation from this, so during this period, 1970 to 1980, something like 1,000 sources were observed, positions were found, structure was found, they were cataloged, published, and so forth. The most interesting thing which everybody what the UT telescope was built for, was to do cosmology and study things like what's happening in the universe. So they looked at all the sources, the size of the source versus the flux. And this is what is now the first statistically significant study of theta S in radio astronomy. And essentially, if you look at this plot here, which is plotting this size of the source against flux, all these low frequencies, all the low flux and low angular size studies are coming from UT. There's one small survey which is isolated here, but nobody believed in it until the UT results show that this is how the shape is going to be. Ideally, in a simple universe, Euclidean universe, you'd expect this to be a straight line, but you can see now that the slope is changing. Again, you need a model which is more than just a steady state. And when they did the statistical study of this, they found that to explain this, you need evolution again, with sources being smaller at earlier epochs. Again, this was proving that this evolutionary model was required. But at this point in the 1970s, most astronomers sort of accepted that the steady state was not really viable. So astronomically, this was not a big deal. But in the local press, it was a big deal because they saw 2 Indian astronomers fighting it out, and so it made a bit of a splash. A number of interesting sources got occulted. They were studied, or papers were published. You can see the source. So 3 components you can very clearly see during one occultation. You can see this 3 components, this another 3 components, different position angles, and you can get things like separation. There are 3 components, and if you look at it, you'll probably find that this is the optical galaxy. And these studies actually were published and printed and go on. But regular observations came to the stop by the end of the decade because people sort of, most of the sources were very boring. There's a lot of effort for observing all these stars and keeping records. And you get only 1 or 2 sources, maybe every few months. And people lost patience, and this thing sort of died. It came to an end. Now, the UT telescope, this occultation takes only about 10 hours a day. So there were other things to be done with the empty time of the telescope. And so some of the big things were, let me just give. One is interplanetary scintillation. If you look at a point source through the solar wind, it twinkles. It scintillates just like a star twinkles when you look at it through the atmosphere. Just like a star twinkles, but a planet doesn't, because different points of the planets smooth the twinkling out. Large sources don't twinkle. Only when sources are smaller than something like 0.3 seconds of arc, which is a second of arc, best resolution at that time was something like a second of arc. Only if a source is smaller than 0.2, 0.3 seconds of arc will it twinkle, because otherwise it gets wiped out because of average. And so if you now make models for the solar wind by studying a source, if you see twinkling or scintillation, you can actually get size estimates and decide how much flux is in the compact component, how much is in the extended. and you start making information, get information about the source. So as a part of this, there was a regular, scintillation project going on. An IPS survey was made of the southern sky. Till then, all the IPS surveys were done in the north, Cambridge. And so this is the first IPS survey of the southern sky. A survey of the galactic plane was done using interplanetary scintillation, and we found that while in the galactic anti-center direction, you could see a lot of scintillating sources. In the galactic center direction, there was no scintillating sources, which showed that there was enhanced scattering of interstellar scattering in this galactic plane, in the galactic center. After about 1990, when the UT telescope was refurbished, it became fast and more sensitive. The interest of using interplanetary scintillation to getting source sizes changed, and rather they use interplanetary scintillation to study the solar wind itself. So there's a whole lot of a whole decade was actually used for studying the solar wind. There are two kinds of studies you could do. One is you point this telescope to one radio source and just monitor it for 10 hours. And once in a while you see things like a transient where some coronal transient event is passing across the line of sight. This is the intensity of the scintillation. This is solar wind velocity, which you can estimate. And you can model this and see what kind of things are happening and correlate it with things happening on the sun. It's another event. It's got a very different shape, and so the geometry is very different. And so this is a thing which you could do. It was done for about a few years. The other thing which has been done is essentially try to get a whole sky picture by studying different sources every day and trying to see how things vary. With the new telescope, which is the enhanced sensitivity, you could study something like 600 scintillating sources at any given time. So the telescope was used to study the 600 sources day after day after day. And if something changed from day to day, you could make models of it to see what is changing in which part of the sky and try to correlate it with things happening on the sun. This sort of interplanetary weather monitoring was very valuable in many ways. It was very interesting. It's the only place which you could do it. But again, it was a very routine thing and sort of it didn't have too much interest for the group. Other projects, you had pulsar observations, the telescope, the large collecting area. So things like the first publication of the UT telescope was actually a pulsar paper where they actually found an error in this measurement properties of this, and they published it locally. There was a pulsar search. They detected some H pulsars. There were studies of interstellar scattering where they had coordinated observation between UT and Australia. So various things happened in pulsars. Spectroscopy was a big thing for some time. They put a limit on the amount of deuterium in the galaxy. They started studying radio recombination lines, essentially lines of hydrogen transitioning in the neighborhood of 270 quantum number, which falls in the radio band. And so this could be detected, and you could make studies of this to study how the interstellar property behaves in different directions. This was largely taken up by the Raman Research Institute and their students. So by the end of the decade, that is the beginning of 1970s, 80s, the interest in occultation died. There were some bit pieces happening in pulsars and scintillation. And so the group started wondering what we should do next. And the obvious thing was the whole radio astronomy world was going to synthesis observations of interferometry and synthesis. There was an absence of, I think they found a escape, sorry. There was an absence of good synthetic synthesis radio telescopes at low galactic latitude and low equatorial, near the equator at meter wavelength. And so the group decided to build a synthesis telescope at UT, what they call the UT synthesis radio telescope. I think you have to change the font, otherwise I don't think I can see it. But anyway, let me continue. So what they did was essentially they had the UT telescope here, and they had 9 telescopes around it, going up to 4 kilometers. Again, we were all stuck with cylinders in those days. So they were all baby cylinders, north cylinder, south cylinder, and so forth. And essentially, you form interferometers between UT telescope and each of the cylinders. Now, if you look at what an interferometer measures, if you think of a source as a two-dimensional function and take its Fourier transform, the interferometer measures one Fourier component of this particular source. So each interferometer measures one Fourier component. As the Earth rotates, the orientation of the telescope with respect to the source changes, so it measures different Fourier components. And so essentially what happens is, at the end of 9 hours of observing, you get a bunch of Fourier components which you measure, you put it on a grid, take its inverse transform, and do some image processing, and you get a map of the source. The more elements you have, the more Fourier components you have, the better is your image. So a bunch of images were studied, sources were studied, and as I said, there's a source, NGC 4631. At high frequencies, a very narrow source. At low frequencies, it becomes much bigger. So you think there is a diffusion of electrons, make models. Galactic plane survey, there was a galactic plane survey, SS 433, W50. Very steep spectrum of source where essentially the source can be seen only at low frequencies. It can't be seen at high frequencies. So it's seen at UT, but not in the other telescopes in the world. So this went on for 2-3 years, but then after that, essentially the interest also died down because it was very hard to maintain. The cylinders which we had, worked on the same principle as the phase shifters of UT, which that electromechanical system was creating a lot of trouble and needed a lot of maintenance. And so they were only 4 kilometers away by the line of sight. There's a deep valley in between, and there's a very poor road system. So often getting to these places was often a big project. And so after about 3-4, maybe by mid-80s, with sort of the imaging stopped and people stopped using the principal telescope. So again, people started wondering what next should we do. So there's a need for a high quality imaging instrument at meter wavelength because all the telescopes which are there at that time were at high latitude and they also had high frequency. And the group had a lot of expertise at low frequencies. So essentially they said, let's think about making a competitive low frequency radio telescope, what they call the giant meter wave radio telescope. Also, the group knew how to make cost-effective antennas. Cylinders were very effective in collecting area. And it was believed that India would be much more radio quiet compared to the Western world because there's not much development. You can always find places where there's no interference. It turned out to be a false assumption because after we built it, cell phones grew everywhere and there were a lot of problems. So by 1984, a draft proposal was made for 36 cylinders of 100 meter size scattered over 30 kilometers. It is also clear when this was all being talked about that you could have the telescope in a place like Ooty. Because close to the equator, the ionospheric scintillation is much worse. It's horrible, in fact. So very often, the nighttime observations at Ooty were washed out by scintillation. And the experts told us that you should have expected this because there's something called the electrojet, equatorial electrojet, which produces a lot of scintillation. So if you want to get decent observations at low frequencies, you have to go north. Now, so leaving Ooty, Bangalore was a necessity just to avoid the ionospheric problems at low frequency. In 1985, there was an IU meeting in Delhi where a lot of astronomers came, and there's a lot of discussion on this telescope. And finally, they all convinced the group that cylinders are not a good way to go if you really want to have high quality dishes, high quality observations. You need to have dishes. So essentially, this dishes versus dashes was the conclusion at the end of the symposium, because cylinders at if they go northern latitudes, have to be at a very steep slope. Or if you make them altizimuth, there's a lot of issues they're not going to now. By 1970, about 30, the proposal changed from this original thing of 36 cylinders to 30 dishes of 45 meters of an inexpensive design. It is not specified. By 1988, the proposal was cleared and funded. The design for the dish, inexpensive dish, worked out. And essentially, during this period, 86 to 89, site surveys were done, and Porter was selected 80 kilometers from Pune. Competing was indoor, it was supported by CAT, but then finally they decided to stick to Pune because it's closer to Bombay. Land acquisition takes place, people are building started at Pune University for the Pune campus and so. And by 1990, construction of the antennas starts. So let me give an overview of GMRT, which many of you know. It consists of 30 antennas of 45 meters, 12 in a central square, and 3 arms, each is about 6 antennas. The idea of having this central square arm is because, as I said, each interferometer measures one frequency component of the source. And to measure large sources, you need short baselines. To measure compact size, you need long baselines. So this is a compromise where you can measure both large and small sources without moving antennas. The dishes were made, if you look at it, they're practically transparent. That is a smart design, smart stretch mesh attached to rope trusses. Normal other dishes, you'll see a lot of circumferential steel members. Here, those steel members are simply ropes. Dishes were connected by optical fiber to the lab, which is the first in radio astronomy, but common now. Large amount of data because of the spectral correlator. And these are essentially, and at the feed, you had 4 feeds you could rotate to bring the focus, and they would observe at these frequencies 150 megahertz, 235, 327, 610, and 100 to 1000 to 1500 megahertz. This is just a picture of construction of the telescope. I'll go quickly. I'll not go into this. We had assistance from various people. And I'll come to the operation. So in 2001, August, GMRT was dedicated to the scientific world by Sri Ratan Tata, chairman of the TIFR Council. And a call for proposals was sent, and every 6 months, the proposals are screened, limited, and time is allocated, and people are known in advance when they're observing so they can plan. The first GMRT cycle started in January 2002, and typically every GMRT proposal call will be oversubscribed by a factor of 2, and you will get about 60 odd proposals, half of them typically from the international community. I'll talk about the science and usage of GMRT. I mean, this is the pie chart which shows who has used GMRT in the first 38 cycles. Currently, the 43rd is running. And I will not talk about the science which is coming out very much because it's a versatile instrument which can be do almost everything you can think of in radio astronomy can do. And typically about 50 papers are published in a year based on GMRT results. All GMRT data, essentially interferomic data, is archived. And the rule is that the proposer has complete rights for it for 18 months, and after that, it is public to the world. Anybody can take the data and analyze it. This is typically a GMRT time observing. If you look at it, all in time slots, different people giving time at different places. This is black is where frequency, the feed rotates. Black is maintenance. There'll be empty slot which you can use if you want. You get the approval of the director. And so this kind of observation is made at the beginning of the GMRT cycle for 6 months in advance. And everybody knows what the telescope is going to be doing for the next 6 months. GMRT started getting upgraded because, as I said, the electronics was very old. And so around from 2012 to 19, most of the systems have been upgraded. The frequency feeds have been modified. The picture I showed you of the eyes of the radio telescope now is completely gone. It's almost completely observable. Observing bandwidth has increased, control systems have changed, all kinds of things are done. And this is how the sensitivity of the UT telescope is sort of changed. You can see that the sensitivity is now sitting over here. And the only thing which is going to be more sensitive is the square kilometer array when it is completed probably by the end of the decade. So UT tells the GMRT is essentially the most sensitive telescope in these low frequencies, and is the premier telescope maybe for the next decade. I'll stop here. And I asked our Dean NCRA, Nitin Kanekar, to give me a list of what he thinks is the 5 most important papers which came from GMRT. I won't even discuss them. I'll just put them up for you to read. If you're interested, we can talk about them. And I will stop here. Thank you.